So now that we've talked about base quantities and derived quantities and formulas, we should also talk about another concept, which is the homogeneity of equations. The homogeneity of equations basically shows that each part of the equation has the same units within it. So for example, if I have an equation, the left hand side should have the same units as the parts on the right hand side, and this shows that the equation is valid and correct. So because I can only compare one type of quantity to the same quantity, I cannot have an equation in which force is equal to power plus acceleration, because they're all different quantities. It's like comparing apples to oranges or bananas and watermelon. We have to compare like terms, so all the quantities within an equation should have the same units. So in order to demonstrate this, you're going to come across some equations within the chapter of kinematics, which is the study of motion. And in the chapter, we look at three main equations known as the equations of motion. Now, the equations of motion are equations that help us solve different quantities of how an object is moving in a straight line. So let's take a look at one of these equations just to demonstrate what homogeneity of equations is. So the first equation that we're going to look at is S is equal to ut plus half at squared. Now S on the left hand side represents displacement, which is the same as distance, which is equal to ut plus half at squared. So ut, now u is initial velocity and it's multiplied by time, and then we've got that being added to half at squared. Half is just a number. Then we've got acceleration multiplied by time squared. So all parts of this equation should simplify to the same units in order for it to be a valid equation. So if I've got S on the left hand side, which is displacement, that means the units on the left hand side are meters, and that means the other parts of the equation should also simplify to meters as well. So if you've got initial velocity into time, the units for initial velocity are meters per second, and this is being multiplied by time. So meters per second into seconds, seconds are being cancelled out, and we end up with meters. Similarly, when we are multiplying acceleration into time squared, then the units for acceleration are meters per second square, and this is being multiplied by seconds square. So the second square and the per second square cancel each other out, and we end up with meters. So if you look at the units, there's meters is equal to meters plus meters. So simplifying into base unit form shows us that this equation is a correct homogeneous equation, and that means it's a valid equation. I can't create or use an equation that has different units in each section. Now we can use our understanding of homogeneity of equations to figure out what the units of a constant within an equation are. So for example, if I have an equation which is energy is equal to constant A into charge Q plus constant B into temperature T into mass M. So I can find out what the constants of this equation are in terms of units, and then I can use those units to figure out what quantities they're referring to. So in order to do this, first I'm going to look at the left hand side, which has energy, and I'm going to equate the left hand side to one of the parts on the right hand side. So energy is equal to constant A into Q. Since the equation is supposed to be homogeneous, then the left hand side should be equal to the right hand side. So in order to find out what the units for constant A are, I'm going to rearrange the equation and take A to one side, and then on the other side I'll have energy divided by charge. And when I do that, I get a certain combination of base units, and these base units represent a certain quantity. And if I look at the table that was given to me within the description, you can see that these quantities are referring to potential difference. So these are the units for potential difference. Similarly, I can do the same thing with constant B. Energy is equal to constant B multiplied by temperature into mass. And when I rearrange this equation, then I end up with B as the subject, and then I can divide the other quantities, and what I get are these specific units. So these specific units then represent what constant B is, and constant B in this case is specific heat capacity. So in this way we can figure out what quantities the constants A and B are representing. So now the concept of homogeneity of equations can also help us to make equations or create equations. So we're going to look at an example here in which you'll have to make an equation, and you might have to come across some questions like this within your practical examination. So for example, say I have a statement which says the dynamic pressure of a liquid of density rho ejected from a pipe with velocity v may be expressed as pressure P is proportional to velocity v to the power of x to rho to the power of y. Given that the constant of proportionality is 0.5, determine the equation. So firstly, let's talk about the constant of proportionality. In this case, it tells me that the constant of proportionality is 0.5. All this means is that we can replace the proportionality sign with an equal sign, and then we can add 0.5, and that would give us the constant of proportionality, which is half in this case. So I'm going to rewrite my equation as P pressure is equal to half v to the power of x rho to the power of y. I can look at the left hand side and the right hand side. I can compare the units and their powers on the left hand side to the units and powers on the right hand side. Now on the left hand side I have pressure, and the base units for pressure are actually kilogram per meter per second squared on the left hand side. On the right hand side we've got half, and then we've got the units of velocity, which are meters per second to the power of x, and then we've got density, which is kilogram per meter cubed to the power of y. So now we're going to look at the left hand side and compare it to the right hand side. So first let's look at one of the quantities, which is mass. So we're looking at kilograms. So if you look at the left hand side, we've got kilograms, which doesn't have any power. So we've got 1 kilogram on the left hand side. This should match the number of kilograms we have on the right hand side. And if I look at my second bracket, which is to the power of y, so y is equal to 1 in this case. Now similarly, I can look at seconds on the left hand side. So it's s to the minus 2 on the left hand side. And if I look at the right hand side, I've got meters per second, which is to the power of x. So I've got s minus 1 to the power of x. In order for the left hand side to equal the right hand side, then x has to be equal to 2. So y would be equal to 1 and x would be equal to 2. So if I rewrite my equation with these values, then I get P pressure is equal to half rho v squared. And in this way I've created my equation based on a statement. So that wraps up quantities and units. We looked at how numerical values are expressed, and then we looked at how they should be written for answers in significant figures. And then we also looked at how units can be broken down into their base unit form and how they work within a formula where one side should be equal to the other side. Thank you for watching the video. I hope it was helpful to you, and I'll catch you in the next one, which will be on the topic of scalars and vectors. Until then, may the force be with you. Really cheesy, but I really wanted to use that line because it's physics.